So let us talk about the water cycle. So as a starting point, let's have a look at a very confined water reservoir. Just think about a lake. So what we're trying to understand now is, well, we have a certain amount of water in our lake, which we call the storage value S. And we want to understand how can it change. Okay, it can change if we add water to the system by precipitation. We call that P. Or it can change by if we remove water from this storage value, evaporation. Okay, call it E. Or runoff, we call it R. All right, a very, very simple example, and essentially what we can work out in the end is the rate of change in storage. That is called delta S here. Okay, which is simply the sum of all the fluxes that we have. P minus E minus R. Okay. And if this sum is 0 on the right-hand side, then we have no change of our storage value. Now, for example, if precipitation is the same as evaporation, and you have no runoff, there is no change of your storage value. And that's important. It's important to understand this principle. Okay, it's important that you understand that you can have precipitation and evaporation at the same time. Okay, so even if you have rainfall, if you have strong evaporation, you get no change. All right, so let's have a look at the water cycle. And we look at the global water cycle. This is shown in this little sketch. And what you can see that there are all different type of fluxes. And we're talking about the ocean, we're talking about the atmosphere, and we're talking about continents. And they're all, and we just look now at the key features. We want to know the global water cycle. Okay? So we'll just put some very simple numbers, not focusing on all the little details or spatial differences. We want to understand the key numbers, the key fluxes. So the first thing we do is we look at the storage values. We look at the water reservoirs. And we compare them. We compare how much water is in these water reservoirs. And the way we can compare them is we just assume if we spread the water reservoir over the entire surface of Earth, what would be the thickness of this layer? Okay, called depth here. What's the depth of this layer? Okay, so that's what's done here. In water reservoirs, we have the oceans. Okay, and if you express that in terms of a thickness, if covered across the entire surface of Earth, the thickness would be 2,650 meters. Okay, you look at how much water is stored in the reservoirs, in the ice caps and glaciers, 60 meters. Okay, if you melted all that ice, the sea level would rise by 60 meters if you spread it over the entire Earth. Groundwater 20 meters, lakes and streams 35 centimeters, soil moisture 12 centimeters, in the atmosphere 2.5 centimeters. Okay, you can work out the total, and then based on the total you can work out relative percentages. And the oceans holds 97% of all fresh water, and you go down to the atmosphere, holds only very, very small percentage. But indeed, water vapor is an extremely powerful greenhouse gas, and although it's a small percentage in the atmosphere, it plays an extremely important role in the climate. All right. Okay, so let's look at the fluxes. The key numbers in terms of the fluxes. And this is what's shown in this sketch. Okay, and the sketch has two parts and the connection between these two parts. On the left side, we're talking about the oceans, and the oceans cover 70% of the surface area. On the right-hand side, we talk about the continents, which have a 30% total coverage of the Earth's surface. So let's start with the oceans. Okay? The surface water balance in terms of fluxes. Okay, so the oceans receive 107 centimeters of rainfall if you spread the rain over the surface of the oceans. Not the entire land, only the oceans. So it's slightly more than 1 meter, 1 meter and 7 centimeters. It receives from rainfall, and the ocean loses 118 centimeters due to evaporation. So on its own, the oceans lose more fresh water than they gain in the absence of the runoff, continental runoff. Okay. And you can also see here over the oceans, the atmosphere gains more fresh water than it loses. And this gain is actually moved over the continents where there's more rainfall falling than water is lost by evaporation. You can see the 75 centimeters here exceeds the 48 centimeters. And we have the runoff that closes the cycle. So it's a closed cycle which consists of the atmosphere taking up water over the oceans and releasing the water as rainfall over the continents. Okay. In case you're surprised why in these arrows here the movement, the atmospheric transport we call it, has two numbers. It has an 11 and a minus 27. The 11 is expressed in terms of the surface of the land. So it's a gain of 11 centimeters if you distribute the water over the surface area of the land. But it's a minus 27 centimeter loss relative to the surface of the ocean. And similar, the continental runoff is expressed in the same way, in case you're confused about this. So this is the key zero-order description of the hydrological cycle. Okay? And here we learn that there's a surplus of water over land, and this is the major ingredient to form life. This is why because we have a surplus of water on land, this is why we have photosynthesis on land and stuff like that. We also learn that the major source of water actually comes from the oceans. Okay, it's the ocean is a major source. On the overland you can think about it here. Indeed, you have the recycling of water. You have a recycling of water, plus you get the water that the new water that comes from the ocean. Anyway, I should not dwell too much on that. We have additional features in polar regions like the carving of glaciers. Glaciers breaking off, melting in the oceans, and so which is not included in this little thing. So let's talk about the Hadley cells and how the Hadley cells influences rainfall and evaporation over the oceans. Okay, shown here a little sketch that I discussed before shows you that over the equatorial zones and the intertropical convergence zones, you have the updraft of moist air, and you create excessive rainfall in this area. Okay, and then you have your return flow, subsiding air masses, sinking air masses, which suppress rainfall at around 30 degrees north and south. You know, you expect dry zones and wet zones. Okay. All right, let's have a look at the distribution of surface precipitation on an annual basis. How much per year? Distribution on Earth. It's shown here in this map. And the map has different colors. Okay, ranging from low rainfall, which is the yellow regions, okay, and the orange regions. Orange is extremely low, to high rainfall, extremely high. And the unit here is in millimeters, so 5,000 corresponds to 5 meters per year. And this is in red. Okay, you have the purple, sort of 4.5 meters, and the blue 3.5 meters per year. And you can look at the distribution, and you can see the distribution corresponds to this map at the top. So you have extreme rainfall in the equatorial regions, okay, and you get a surplus of, you get the green regions at higher latitudes. You can see that here at mid latitudes. All right. Plus, there are some additional features. You know, you can see there's another convergence zone, which is called the subtropical convergence zone, which is a key feature which runs along here. You can also see some high rainfall regions, you know, which are actually aligned with, we call them westerly boundary currents, western boundary currents in the ocean, like the Gulf Stream. You can see that here. Anyway, so that's the pattern of rainfall. Okay, and there's a rainfall. You know, there's rainfall everywhere, but the intensity varies. And now we have to compare it with the precipitation. So let's have a look at the precipitation. Not in a map. I'll show you maps later on, but just look at, for simplicity, just a distribution from the South Pole to the North Pole. And these are these curves here. From the South Pole is minus 90 here. Minus 90 degrees is the South Pole. The equator is in the middle, and the North Pole is here on the right. And you can see 3 curves. The black thick line is the precipitation curve. You know, you see that this distribution, which has a maximum in the intertropical convergence zone. Okay, you can see that it has a minimum. You know, it has a minimum. And this is now here in centimeters per year, okay? It has a minimum in these areas here and a maximum. Okay, and the dashed curve is the evaporation curve. Okay, you can see the evaporation. Okay, and evaporation is a strong function of the surface temperature. That's why you get a higher evaporation, because in the warmer regions, you know, the atmosphere can hold more water vapor, okay? And it also induces a higher evaporation in these areas. And the difference is called delta F, and it's P minus E. This is the difference curve here. So you have regions where you have an excess of rainfall, okay? And you get it near the equator, and you get it at mid-latitudes, around 60 degrees north and south. And you have regions where you have a deficit. You're losing water to the atmosphere. It's a rainfall deficit. Okay? This is where the atmosphere gains water from the oceans. And it's between 15 and 45 degrees, something around that in both hemispheres. And these are the dry regions over land. Okay? So let's have a look at a map, a distribution, and this map shows you evaporation minus precipitation. It's the other way around. The regions where you have positive numbers are the regions, the yellow regions, where you have an excess of evaporation. Okay. And have a look at that. You can see these vast regions in yellow here, north of the equator, south of the equator. Okay. And we talked about the latitude range. At mid latitudes, you get a surplus of rain. You know, you get surplus of rain, northern and southern hemisphere, and surplus of rain in the intertropical convergence zone. And as I mentioned before, this South Pacific convergence. Yeah, it's another region here. Noting that you have strong seasonal variations due to the monsoon here in the tropics, subtropics regions in the eastern Indian Ocean and western Pacific region. All right, so that's the link of the atmospheric circulation to rainfall. You notice some other fine details, and we also mention that here again. You can see that if there are mountain ranges, you know, you get very strong rainfall on one side, and on the other side you have little rainfall. Okay? There are so-called rain shadows. Okay? Some significant features too in this map. So now you can use that knowledge and put it together, and you can now discuss how deserts are formed. And there are different types of deserts, essentially two different types of deserts. And we're also including the transition of semi-arid zones, steppe, where we also include that. It's also shown in this map, which are adjacent to the deserts, you know. And then we have two different types. We have subtropical deserts, which are linked to the subsidence zones of the Hadley cells, where rainfall is suppressed, where we have sinking air suppressing rainfall. Okay. We have mid-latitude deserts, which are sheltered in deep interiors of large land masses, far removed from ocean moisture, and rain shadow deserts. Okay, and this is how you can explain these desert zones that we have on Earth. Okay. All right, and indeed we are interested to know how will the extent of these deserts change under the influence of global warming. Okay, will they shift in location? Will they become bigger or smaller? Okay, stuff like that. So as the last slide of this part of the lecture, just a memory of what rain shadow deserts are. And this is just a little sketch here showing rain shadow deserts where you have winds bringing moist air from the oceans, moving them over the land, inducing a vertical motion in the atmosphere because of the topographic effect. The air is forced upward, cools down, condenses, creates clouds and rainfall. And then on the other side, you have no more water left in the atmosphere, and you have a rain shadow and a desert on the other side. On the leeward side, you know, I have much drier air. And this concludes the second part of this lecture.